Alright, in this video we're going to be working BC Homework 6.1. So we're going to do some Riemann sums and we're going to work with some integral properties. So we're going to start with, here's a table, let's do a Riemann sum on it. So we're going to do a left Riemann sum, so that means that we're going to add up the area of a bunch of rectangles and we're going to get our heights from the left edge of each subinterval. Okay, so my subintervals are the ones indicated by the data in the table, so that's 0 to 2, 2 to 6, 6 to 7, and 7 to 12. And so I'm going to start in and say, the integral from 0 to 12 of f of x dx is going to be approximately just width times height plus width times height, over and over again. Okay. So the first width is 0 to 2, it's the difference in my x's, and the height I'd get from the left edge of the subinterval, so that's going to be 11. Then from 2 to 6, that's a width of 4, and I would get the height from the left edge of 2 to 6, which would be at x equals 2, that's going to be 10. Then from 6 to 7 is a width of 1, height 8. And then 7 to 12 is a width of 5, and the height is also going to be 5. And I could, put these numbers all together and simplify them, like 22 and 40 would be 62, and 8 is 70, 95. But you don't have to, right, because this is AP calculus. But I will say, a problem like this, very likely a multiple choice question, and on one of those, you would have to simplify your answer. And then as to whether or not I'm more likely to be an overestimate or an underestimate, let's see, let's look at the values of f. Okay, 11 to 10 to 8 to 5 to 3, f is decreasing. Okay, so f, I guess I don't know that because there's not like a whole lot of info about f besides its values at these selected points. So I'm going to say f appears to be decreasing. Okay. And that would indicate to me that the approximation left Riemann sum on a decreasing function, if I, like that's going to be an overestimate. Okay. So I'll say more likely an overestimate. But without, further information about, the certainty of whether f is decreasing, we could not say for sure. All right. Number 3 says, let's write a definite integral that represents the area of the shaded region and then evaluate that integral using geometry. So for A, okay, this is a horizontal line at y equals 3. So I'm going to find the area under the graph of f of x equals 3 as x runs from 0 to 5. Okay, and that's a rectangle with width 5 and height 3, so that's going to be equal to 15. Okay, next one is a line going downhill. So it's starting at 4, and it looks like the slope would be negative 2. So that's going to be 4 minus 2x, and x is going from 0 to 2. Okay. 1/2 base times height, 2 times 4 is 8, divide by 2, that would be equal to 4. And then this one's a little bit trickier because this is, it's like, I can see it's a triangle. I know whatever integral this is going to be, it's going to go from negative 4 to 4. And that the width was 8, height was 4, so this area is half of 32. Really, the question is, what am I going to put on the inside of my integral? Okay, and so if you see, it's kind of like an upside-down V shape. And when x is 0, I've got an output of 4. X is negative 4 or positive 4, I've got an output of 0. Think it's going to be 4 minus the absolute value of x. That whole, looking at a graph and modeling a function, that's one of those kind of precisely the skill we don't build in K-12 math. So that's, that might be a little bit beyond the scope of what you'd be asked to do on a quiz or a test. The next one's talking about a midpoint Riemann sum. With a midpoint Riemann sum, I'm always going to recommend that you kind of draw out the interval and kind of map it to make sure you're getting your correct midpoints. So we're going from x equals 0 to x equals 2. So I'm going to just draw that. And 2 subintervals of equal length. Okay, so each subinterval is going to have width 1. And we want to use a midpoint sum. So my midpoints of each subinterval are going to be 0.5 and 1.5. Meaning, if I want to, approximate the integral from 0 to 2 of 4 to the x dx. Okay. Each width is going to be 1. And so our job is to figure out what the heights are going to be. So the height is going to be the output of 4 to the x at 0.5. So 4 to the 0.5 and 4 to the 1.5. And again, technically, I guess this would be a safe place to stop because this is, all numbers. But man, this is going to, if I was going to ask you this question, it would be in multiple choice. And so you would need to be able to figure out, 4 to the half power is the square root of 4. So that's 2 plus 4 to the 1.5. Okay, well, that would be 4 to the 3/2 power. You take the square root and then cube that. 8. Okay, so 1, 2 plus 1, 8 is going to be 10. So this is, approximately equal to 10. Right? Giving a sketch of the region whose area is given by this definite integral. Okay, 0 to 4 of x dx. So I'm thinking about y equals x, drawing a sketch of that. Y equals x, you should be able to draw that one. From 0 to 4, this region right there. Okay, now use geometry to compute the integral. Okay, the width is 4, the height is going to be 4, so this area would be half of 16. That's going to equal 8. Then 2x plus 5. Okay, so that's going to be a line, and it's going to start at 5, and it's going to have a slope of 2, and we're going to go from x equals 0 to x equals 2. Okay, so that's x equals 2. This is going to be my area. Okay, you could do this as a trapezoid where the bases are 5 and 9, and the height is 2. If you wanted, we're talking about trapezoids today, so that's definitely an option you've got. Me personally, I think I'm going to just go ahead and label all of this. Okay, a height of 5 and a width of 2, that's going to be 10. And this triangle is going to have a height of 4 and a width of 2, so half of 8 would be 4. And so I'll say the integral from 0 to 2 of 2x plus 5, that's going to be 10 and 4 is 14. And the next one, the square, whoops, I copied down a number wrong. Okay, oh goodness, I think I'm afraid I've already ordered the copies on that one. But you're going to need to change that from -3 to -5 because it wouldn't make sense otherwise. You would not be able to do it, especially with the tools you have right now. We don't really have any techniques to compute these besides using geometry. Okay, so it needs to be -5 to 0. But the square root of 25 minus x squared, that's a semicircle. Because it's the positive square root, it's the upper half of the semicircle, and it's going to be centered at the origin and have radius 5. And that is an equation type we need to be able to recognize and know what the graph looks like in this class. And so this would be 5, and that would be -5. And if we're integrating from -5 to 0, it's just going to be this part in the second quadrant. And so this integral is equivalent to the quarter of a circle. So, okay, so 1/4, so this is going to be equal to 1/4 of pi times radius squared, and so that would be 25 pi divided by 4. Right, and then the last one, I like this one, 2x minus 4. Right, so it's going to go up like that, and then it's going to go from 0 to 4. Well, this is at 2 right here, and at okay, so if you plug in x equals 0, you would get -4, and if you plug in x equals 4, you would get +4. So I'm trying to show you that these areas here are the same, and they're going to balance each other out because this one's underneath the x-axis, it counts negatively. This one's above the x-axis, it counts positively. This integral is going to equal 0. Right, now we're going to move on and do some integral properties. So the graph of f is shown above. Area of A is 1.7, but the integral from 0 to 2, that's going to, okay, yeah, that's the first thing we're going to do. That's going to count negatively, so I might as well just get in there right now and say, okay, if the area of A is 1.7, then really the integral from 0 to 2 of f of x dx is -1.7. Okay, the integral from 2 to 8, that's what we're going to have to figure out. The whole integral here is 7, but this counted negatively. So I think that this would need to be 8.7 because 8.7 plus negative 1.7, that adds together to equal 7. And then the integral of f of x plus 2. Okay, so we're going to need the integral from 0 to 8 of f of x and then add 2. I'm kind of realizing I had set up these problems. I guess I'll just write on the problems this time on this page because I kind of put these in a certain order. Okay, so these were, both pretty straightforward. The integral from 0 to 2 of 3 f of x is going to be 3 times the integral from 0 to 2 of f of x dx. And so that would be 3 times negative 1.7 is going to be negative 5.1. Okay, the integral from 8 to 2 is the opposite of the integral from 2 to 8, so this is going to be the negative of 8.7. Okay, and then now this one, this is where we're going to start adding stuff on, and it's going to get a little bit more complicated. So I've got f of x plus 2. And I think what I would recommend that we do is split this up into 2 integrals. That's one of our properties. Okay, this is going to be a rectangle with height 2 and width 8. So I'm going to add 16 to it. The integral from 0 to 8, we already knew that. That was 7. So 7 plus 16 is going to be 23. And then 2f of x minus 5 from 2 back to 0. Okay, so what I'm going to do is I'm going to say, well, that's the integral from 2 to 0 of 2 times f. Minus the integral from 2 back to 0 of 5 dx. Okay, so especially because we're new to this, I might just go ahead and say, okay, we're going to do this one with geometry. This is backwards. I should say, kind of just reverse the bounds and make the integral negative. Okay, so now it's positive. Okay, so height 5, width 2, that's going to be 10. 2 times the negative of this, so that would be 2 times positive 1.7 would be 3.4, and that would be 13.4. That's always good set of examples there. Like that. Use a trapezoidal sum with subintervals indicated by the data in the table to integrate from 2 to 13. Okay, this one really didn't print very well. So this is going to be approximately equal to the width, and then we average the heights. Okay, and so if you can mentally average them, then just go ahead and do that. Feel free to. But if you don't want to do that, just 1 plus 4 divided by 2. Then the next width is 2, 4 plus negative 2 over 2. Then 5 to 8 is a width of 3. Negative 2 plus 3 because we're averaging. So I'm just going to add and divide. And then 8 to 13 is a width of 5, and average 3 and 6. And if you know that's 4.5, great. But if you wanted to say 3 plus 6 divided by 2, that's the exact same thing. And I'm really going to recommend we leave this one unsimplified. I have to go find my next pages. Printed out of order. Okay, there we go. Number 8. The velocity of a particle moving along the x-axis is modeled by the differentiable function v, where v is measured in meters per second and t is measured in seconds. Okay, so I'm just going to do some position, velocity, acceleration work. Let's see. It needs to refocus. Maybe it's a little better. So estimate the acceleration. So we're going to do some rise over run, find where 36 would most likely be. Okay, that would be right in here in this, part of the table. So I'm going to say, all right, acceleration at time 36, that's equal to the derivative of velocity at time 36, which is going to be about, we're going to do rise over run, 7 minus negative 4 over 40 minus 32. So it would be 11 over 8. 1.375, but 11/8 does the job just fine. And then indicating units of measure, the derivative of v should be meters per second divided by seconds. Okay, meters per second, meters per second squared. However you want to write that, it really doesn't matter. You can write in words, you can write in symbols, whatever you like. Okay. Now, using a right Riemann sum with the 3 subintervals indicated by the data in the table to estimate 20 to 40. Now, you got to be careful, and I did this a couple times in this homework because I've seen this. We've seen this in AP Calculus, where they actually only want you to do a subset of the table data that they gave you to integrate. And if we're integrating from 20 to 40, we're really going to only need this stuff. So we're going to use a right Riemann sum. So, 20 to 25 is a width of 5. And the height we're going to get from the right edge of that subinterval. So that'll be at t equals 25. Height, -8. Then plus 25 to 32 is a width of 7. Right edge is -4. Plus 32 to 40, the right edge of that, I'm going to be multiplying by 7. And, all right, again, you can do that if you want. I think that's -14, but I'm going to leave it unsimplified. Now, using appropriate units, interpret the meaning of this integral in terms of the motion of the particle. And this is going to be tough. But I've got it where the velocity is negative and then positive. And we even saw that in our Riemann sum. So it's like, okay, and the negative and positives we're kind of adding together. And I forget, if we think about the units of measure for the integral, we've been multiplying meters per second by seconds. There's definitely that. So I think that's definitely the thing. If we're gonna, if we're finding an integral and we think about one little unit square under there, if this is measured in meters per second and this is measured in seconds, and 1 meters per second times 1 second, that's a meter. Okay, right in here, each square is a meter. And then when velocity went underneath the t-axis, those were counting negatively. We were moving to the left. And so really each of these squares is like, 1 unit of our motion. And so this integral represents the change in position, which is not exactly the same as the distance traveled. But we'll talk about that so much more later in this unit. I'm not really all that concerned with the meaning yet. Okay, so I'm going to tell you what it is. The change in the particle's position measured in meters from time 20 to time 40 seconds. I don't know if I've talked to you this, your class this year about the nut strategy when we're doing an interpretation, but we need a noun, units of measure, and a time element. And we've got that. Noun, change in position, units of measure in meters, and time element t equals 20 to t equals 40 seconds. We need all 3 of those. All right, number 9, now we've got a rocket. Rocket A has positive velocity after being launched upward from an initial height of 0 feet at time t equals 0. The velocity of the rocket is recorded at various times during the first 80 seconds of its flight. Now, use a midpoint Riemann sum, so we're going to do another one of those. I felt the past few years that students in my class felt underprepared on midpoint sums. They're very rare in AP calculus, but they shouldn't be hard and they shouldn't be anything we're scared of. That's why I just put it on here twice. All right, so 10 to 70. 3 subintervals of equal length. Well, we've got a width of 60 from 10 to 70. We're dividing it in 3, so it should be 20, 20, 20. So 30 and 50, and if I'm looking for the midpoint, okay, halfway between 10 and 30, that's going to be 20. So the actual heights of my rectangles, I'm going to be getting from t equals 20, t equals 40, and t equals 60. Okay, so and that's my 3 subintervals, so this integral is approximately equal to, all right, 10 to 30 is a width of 20. I'm going to get my height from t equals 20, which is 22, plus, okay, 30 to 50, another width of 20. Height at 40 was 35, plus, okay, 50 to 70, another width of 20. Height was 47. And that's going to be, my approximation right there. That's great. Did a midpoint Riemann sum. But then we can do something else, kind of take it back to the last unit and say, rocket B is also launched upwards. Its acceleration is given by A is equal to 3 over the square root of t plus 1 feet per second per second. Time t equals 0, the velocity of B is 2 feet per second. Which of the 2 rockets is traveling faster at time t equals 80? So what we need to do is write an actual formula for the velocity of rocket B, and then we'll, using anti-differentiation, and then we'll just compare to 49. Okay, the velocity of A is 49 at 80 seconds, and so we're just going to keep that in mind. The velocity for B should be an antiderivative of 3 times t plus 1 to the negative half power with respect to t. We can do that. We're going to just use power rule. Might be a little careful about the chain rule because we've got the, interesting inside of our power. But it's really the slope of the inside's 1, so it's not going to be a big deal. We're going to add 1 to the power and then divide by the new power. And so that would be divided by half is multiplying by 2, add a plus c, and definitely check to make sure, on a derivative level that this is working. So if I take the derivative of 6 times t plus 1 to the half, I'm going to have half of 6 is 3. That's promising. T plus 1, subtract 1 from the power. Yes, I like that. Then multiply by the derivative of t plus 1 with respect to t, and that's multiplying by 1. So, yes, I'm right where I need to be. Okay, so I'm going to figure out the value of c. The velocity is 2 when t equals 0. And we know any power of 1 is going to be 1. So that looks to me like c equals negative 4. So velocity of b equals, out of sight now, but let's move this up, 6 square root of t plus 1 minus 4. And so if I wanted the velocity of b at time t equals 80, that would be 6 times the square root of 81. Oh, I know how to take that. Minus 4. 6 times 9 is 54. Minus 4 is 40. Or no. 54 minus 4 is 50. Oh, 50 versus 49. Okay. Rocket B is traveling faster because 50 is greater than 49. The A of 80 was equal to 49, and I would say B is traveling faster. Okay, now for the last page, here we go. A spherical balloon is being inflated. Okay, yes, I've used this. I've probably already used this table on y'all. We've done this with a cone, but I can switch it up to a sphere, and we can do Riemann sums, and also maybe a little bit of related rates. Don't you forget about that either. So let's use a trapezoidal sum in the 3 subintervals indicated by the data in the table to approximate the integral from 0 to 7 of r prime. Okay, so another trapezoid. 0 to 7. Okay, so we're going to stop there. So yeah, only 3. 0 to 2 is a width of 2. We're going to average 5.7 and 4.0. 2 to 5 is a width of 3. Average of 2 and 4, we can do that. And then 5 to 7 is a width of 2. 2 plus 1.2 divided by 2. If you've got that, good for you. If not, you can just leave it unsimplified, and that'd be totally fine. That's going to be, just what we need. Is my approximation greater than or less than the true value of r, or the integral from 0 to 7 of r prime of t dt? Give a reason for my answer. Well, okay, we're definitely going to be going to these pieces of information right there. I think I'm going to try to draw the graph of r prime. So r prime is positive. It's decreasing. And then we're saying, okay, that makes sense with r double prime being negative. R triple prime is positive. So that means that the graph of r prime is got to be concave up because the second derivative of r prime is positive. So positive, decreasing, concave up. That's my graph of r prime. And then if I do a trapezoidal sum, just with one subinterval, I can see that it's going to be an overestimate. So I'm going to be saying it's an overestimate. The reason is the curvature of the graph. Had it been decreasing but concave down, then the trapezoid would have sat underneath. So it's really the concavity of the graph of r prime. The reason, though, is that we said that r triple prime is greater than 0 for all t in the interval 0 to 7. You could say 0 to 12, and that would also be true, but 0 to 7 is what we need. All right, and then at t equals 7, the radius of the balloon is 40 feet. What is the rate of change in the volume of the balloon? So it's dv dt. And so we're going to take the derivative of this with respect to time. Just long enough. I think you might have been about to forget about related rates, and I can't have you forgetting about related rates. So we're going to multiply by 3, and that'll be 4. Pi radius to the 2. We subtracted 1 from the power, but we do need to multiply by dr dt for the chain rule. And now dr dt, we're going to be able to find that from the table. That's going to be at t equals 7. dr dt was 1.2. So equals 4 pi. Radius squared would be 40 squared. And then dr dt was 1.2. Okay. Now, that's going to be a perfectly suitable answer. Yeah, because I don't know 48 times 16 or 4.8 times 16. That's going to be risky for me, so I'm just not. And the last one we got here is number 11. Just some geometry here. So this one also. Oh no, this one printed fine. It just does not look very good on the document camera, but that's no big deal. The graph of f is consisting of 2 line segments and a quarter of a circle, as we can see. The integral from 1 to 1, well, of any function, that's going to be equal to 0, okay, because there's no area right there. The integral from 2 to 5, okay, that's going to be a little bit trickier. I had to make sure I had one of these on the homework, though. So if we go over here, this whole square has an area of 9. And I'm going to have to subtract away that quarter circle to get what's in here. So I'm going to say that this is 9 minus 1/4 of pi radius squared. And it does look like the radius is 3. Okay, so I could say 9 minus 9 pi over 4, or that is a perfectly suitable answer. Okay, negative 2 to 2 of f. Okay, well, I could say I've got a positive half here and a negative half here. That's going to balance out and add to 0. That's a quarter. It's a negative quarter, and that's a positive quarter, so those are balancing out. So really from negative 2 to 2, all I've got is this business right in here, and I think you can, just by, geometry, moving pieces around, this one would fit right there. That area is going to equal 2. So I've got a net total of 2 there. And then from negative 2 to 5, well, that would be from negative 2 to 2 plus 2 to 5. So that should be 2 plus 9 minus a quarter of 9 pi. So I'm going to call that 11 minus 9 pi over 4. Now, the last problem we've got here is find the values of k that make the integral from negative 2 to k of f of t dt equal to 0. Okay, well, one I know immediately is k equals negative 2, right? Because as I showed you up there, and probably talked to you about earlier, the integral from anything to itself has to equal 0. But I think we saw there's another place where this could happen. Right, we balanced out. I remember thinking about it at t equals 0, we had balanced area. So if we integrated from negative 2 to 0, we would have a net 0 amount of area. And then if I keep going, eventually I have another balanced out point, so that would be k equals 1. That was interesting. Usually this problem type, we would do this one more algebraically once we learn how to actually take an integral, which you'll learn about in class next time. But that was a little different. I enjoyed that. This was a solid set of problems. I think it was a lot better than the old problem set I had for Riemann sums. So that's going to be all for this video. Thanks for watching.